Assalamu alaikum. Hope you guys are doing great, safe and sound, and everyone connected to you is also safe and sound. Okay, let's start the new topic of electrostatic. Electrostatic is a simplest possible case of electromagnetics, where we study the effect of static charges in their surrounding. And fortunately, so far we have discussed more simpler case in the electrostatic, that we have studied static charges in the free space. In this regard, we have discussed Coulomb's law, Gauss's law, and scalar electric potential. In these topics, we study that how electric field, because of the static electric charge, could be find out in the given scenario. Okay, so it's in the nature or in the physical life, it is always not possible that effects of charges are only because of the free space. Most of the cases deal that you have to put your experimental setup, or you have to encounter with different material mediums. So today we will start studying that how static electric field will be affected when it is placed in the conductor, dielectric medium, and how resultant electric field or resultant electric quantities or formulas that we have already discussed, for example fundamental postulates of electrostatics in the free space that we have discussed in the first lecture of electrostatic, how will they affect in this scenario. Okay, and before going to start today's topic, let me introduce some new terms which are tangential and normal components of electric field, or tangential and normal components of any field. These are the most used or very frequently used terms in the electromagnetic world. So as we know that electric field or any vector in the coordinates or orthogonal coordinate system has three components. Okay, if it's Cartesian coordinates, then it is Ex plus Ey plus Ez and whatever. Okay, so when we are dealing with the surfaces, you know that surface constitutes of two dimensions. One of the component is not present in the surface. You know very well. Okay, so let me try to demonstrate it with the use of this geometry. Let's say it is a 3D geometry. As you already know that the sides towards you is considered as x-axis in the classroom. This side is the y-axis, and the height side is the z-axis. Okay, so based upon this coordinate system, it has 6 different faces: 1, 2, 3, 4, 5, and 6 one. Okay, for every surface, tangential components, or every surface is constitutes of 2 of the components, as I was saying. For example, let me consider this upper face. Okay, when moving from any point to any other point, I might have to travel in the x and y plane according to the scenario coordinate system that we have that we have already defined and just discussed. Okay, so moving from any point to any point on this surface will not change the z direction, right? While moving on this face, okay, from this to this point, there will be change in the z and there will be change in the y axis. Okay, but there is not any change in the x-axis. Contrary, when moving on this face, let me do it in this side. Okay. When moving on this face, there will be change in z and x-axis, while there is no change in the y-axis, right? Same is the case. It is a very simple term, tangential and normal component. Unfortunately, as it depends on the surfaces, that's why sometimes it becomes difficult to understand. But if you have a clear concept of surfaces, like we just have explained. There will be no problem for you to distribute to distinguish between tangential and normal components. Okay, for example, again consider this upper surface. Those electric field components or those field components which are propagating along this surface are called tangential components. Okay, let me rephrase it. वो तमाम components जो कि इस सरफेस के साथ साथ चल रहे हैं, मिसाल के तौर पर इस पर अभी अभी हमने देखा कि x और y में चेंज आ रहा है, ठीक, तो इस सरफेस को इलेक्ट्रिक फील्ड का x कंपोनेंट और इलेक्ट्रिक फील्ड का y कंपोनेंट जो है वो मुतासिर करेगा या इसके ऊपर असरअंदाज होगा. सो इसीलिए इस सरफेस के लिए जो टेंजेंशियल कंपोनेंट्स जो इसके साथ साथ चल रहे हैं, पैरेलल टू इट और along it, those are called tangential component. Whereas the component which is normal, and you know normal component to this is the z component, okay, either in this or either in the this direction. So this is the z direction. Z component for this surface is in the normal direction and called normal component of tangential or normal component of electric field. Okay, please practice it for some other phase. Let me give demo for another phase. Let's discuss this surface and please tell me in the taskbar that how you can find the tangential normal components. Okay, for me, if the surface is in this direction, okay, x, y and z, tangential component of electric field on this surface, okay, are x and z, while y is the normal component. Okay, that's it. Y is the normal component for this phase. अब प्रॉब्लम या एक छोटा सा और मसला क्या है कि हर फेज के लिए टेंजेंशनल और नॉर्मल कंपोनेंट्स डिफरेंट होंगे. ओके, बिल्कुल इसी तरह जिस तरह हर फेज के लिए आपके पास जो है वो x और y या जो दो कंपोनेंट्स है वो डिफरेंट है और एक उसके ऊपर नॉर्मल कंपोनेंट है. So life is simple, make it simple. Tangential and normal components were introduced and these are very easy things to digest. Okay, let's start today's topic. First of all, let's place a conductor, kind of slab of copper material, aluminium, whatsoever, in the static electric field domain and see what happens to them. Okay, for example, consider that we placed some positive or negative charges in the interior of the conductor, or we could also produce some external electric field in both cases. Okay, when we will produce some positive or negative charges in the interior of a conductor, there will be an electric force. Okay, there will be force which will force or push the nearby charges, and the charges will automatically transfer or move towards the surface of the conductor. Okay, let me just give you, okay, it's also a surface. You could consider again this geometry, that it is you have to assume that it is a conductor, and we place in the center of we place some charges in the center of the geometry, and they will push or force electric field on other charges, and all of the charges are on the surface of the geometry. Okay, so what about interior of this conductor? We don't have any charge density. Okay, we don't have charges in interior of a conductor. So according to the Gauss's law, E dot d of surface integral or rho is equal to 0, and consequently electric field will be equal to 0. So static electric field in the interior of a conductor will be equal to 0, and so the charge density as well. In both cases, either you introduce or you place some charges, positive or negative, inside the interior, or you excite or you hit some static electric field on this conductor, or you place the conductor in this electric in the electric field environment. Okay, so at the next step, let's find what happened to the surface. Okay, all the charges are on the surface when the conductor is placed in an electric field region. Assume that there are tangential components of static electric field produced by these charges. Then again these charges will force each other and insert force on each other, and resultantly on the surface this charge distribution will not be in equilibrium state. Okay? जब ये फोर्स आपके चार्जेस के ऊपर, सरफेस के ऊपर रखे हुए चार्जेस के ऊपर भी वैसे ही टेंजेंशनल डायरेक्शन में अगर फोर्स लगे, मिसाल के तौर पर ये हमारा सरफेस था जिसके ऊपर चार्जेस इस वक्त आ चुके हैं, ठीक, और अगर ये एक दूसरे को पुश करते हैं, सेम फोर्स लगाते हैं, देन दीज विल नॉट बी इन द इक्विलिब्रियम। जबकि एक्सपेरिमेंट शो करते हैं कि सरफेस के ऊपर, कंडक्टर के अंदर सरफेस के ऊपर जो है वो चार्जेस इक्विलिब्रियम स्टेट में होते हैं। तो जब हम इस चीज को, इस एक्सपेरिमेंटल वैल्यू को अपनी इक्वेशन फॉर्म में लिखते हैं तो हमें ये मानना पड़ेगा कि टेंजेंशनल कंपोनेंट ऑफ द इलेक्ट्रिक फील्ड ऑन द सरफेस, ये बात थी इंटीरियर की, सरफेस पर भी जो टेंजेंशनल कंपोनेंट्स हैं वो जीरो है। अभी हम इसको मैथमेटिकली भी देखते हैं। सो फिर इलेक्ट्रिक फील्ड जिसके अभी हम बात कर रहे थे, तो इट कंस्टिट्यूट्स ऑन थ्री कंपोनेंट्स। लेट्स सपोज 2 and 3 are the tangential components, which is equal to 0. So we have to claim that electric field on the surface of a conductor is only in the normal direction. For this phase, for this phase, for this phase, electric field is only in this direction. Okay, so let's find it with the help of mathematical calculation. Okay. Let me consider. First, let's discuss tangential components. Okay, in case of tangential components, let's draw a closed path, a contour on the border of the conductor and free space. For example, this is a conductor again, and I want to find out the tangential component on this surface. Okay, so I draw a contour at this half of the contour, half of the closed path is in the conductor and half is in the free space, like this. Okay, so let me name A, B, C, D. We know that static electric field is curl free or irrotational, like this, fundamental postulate of electrostatic. Okay, now this contour means A, B, C, D. If I did if I do integration on this path starting from A to B, AB E dot d of L, which will be B minus A, and which is the width of this box that I have drawn on this patch. Okay, so E delta, right, when we integrate. On the other hand, when I integrate this phase, again E dot d of L, but this portion is in the interior of the conductor, and we have already said that in the interior electric field is equal to 0. So this part will not contribute in summation of this integral. AB plus DC plus CD plus DA. Okay, four integrals will give me that contour integral. As you have already done, that's why I am just passing by the things. Okay. So what about this and this face? This and this face, we have drawn this cube having negligible, approximately equal to the 0 height. For example, as compared, this height approximately 0 or negligible is with respect to the width. Sorry, height is very less than the width. Okay, so for example, if width is 5, what's up the unit? And it will be 0.2. If it is 0.2, then this portion will be 0.1, this will 0.1 minus 0.1, oh sorry, 0.2 and 0. Now that is very less, so that we can ignore it, or we could we are okay if you want to consider the contribution of this part is okay, very thin slab. So we are just left with this expression, contribution of the face which is in the free space. Okay, this one. Okay, and you know this face is in the direction of this surface, so it is the tangential. This surface, this component is propagating along this surface, so it is called tangential component. That's why it's good to put T. Now either this term should be equal to 0, either this term should be equal to 0. This is the physical term, it is a width that we have drawn, so it should not be equal to 0. So this, at least, okay, tangential component of electric field at the surface of a conductor which is placed in the static electric field is equal to 0. Okay, let's see what happened to the normal component. This time, as I have to deal with the normal component and Gauss's law. Okay, second fundamental postulate. First fundamental postulate we have used to find out the tangential component, and it was appropriate to the geometry. This formula was appropriate to the geometry, and this time Gauss's law is appropriate to our geometry. We are interested in normal component. Okay, let's consider this upper face and draw a Gaussian surface on this. We draw the Gaussian surface like half of the Gaussian surface is in the free space and half of the Gaussian surface is in the conductor, just like we draw a closed path, a contour like this. Okay, that was a closed path, a linear closed path, but this time we have a surface. Okay, so again there will be contribution from the top face, from the down. Gauss's law states E dot d of s, surface integral, that is equal to amount of charge placed on the surface. Okay, if you are interested in total charge, then you have to integrate on the volume, or rho s delta. S is surface. Okay, while on the left hand side, E dot d of s, electric field itself. When we integrate double integral, let's say it's 0 to x, 0 to y. Okay, it will give me xy, right? And xy is the area of this top face or whatsoever we are dealing, top face or bottom face. Bottom face will also not contribute, just like we did, because electric field in the conductor is equal to 0. Okay, so bottom face will have 0 electric field, so it will not contribute. Only upper face, which is in the free space, it will contribute. So E it's delta of s. Okay, a very small chunk of the a surface. As this dot will produce only single normal component, okay, this one. So this label as so normal component of electric field okay. These equations are also called boundary conditions. Boundary means when we will travel from one to other medium. Fortunately, other medium is a free space. So when you place a conductor, we are only discussing conductor at this moment. When you place a conductor in the static electric field, then electric field going from one to other medium, going from conductor to the free space, will obey these conditions, that tangential component will be equal to 0 and normal component will be equal to the amount of charge spread or amount of charge aligned on this surface. ओके जी, लेट मी फ्रेज. हमने अभी तक ये डिस्कस किया कि अगर आप एक कंडक्टर को किसी स्टैटिक इलेक्ट्रिक फील्ड इन्वायरमेंट में रख देते हैं या उसमें खुद से स्टैटिक इलेक्ट्रिक फील्ड प्रोड्यूस कर देते हैं, दोनों सूरतों में, तो इंटीरियर ऑफ द जो कंडक्टर है, कंडक्टर की इनसाइड पर ना तो कोई चार्ज होगा और ना ही कोई इलेक्ट्रिक फील्ड होगा. सारे का सारा चार्ज चला जाएगा सरफेस के ऊपर, ठीक है. और सरफेस के ऊपर फिर फील्ड, इलेक्ट्रिक फील्ड, उन चार्जेस जो कि सरफेस के ऊपर आए हैं उनकी वजह से चार्जेस, उनकी वजह से इलेक्ट्रिक फील्ड की वैल्यू क्या होगी, तो उसमें भी इलेक्ट्रिक फील्ड के 3 कंपोनेंट्स में से सिर्फ एक कंपोनेंट की वैल्यू आएगी और वो कंपोनेंट होगा जो कि आपकी रिस्पेक्टिव सरफेस के नॉर्मल होगा. अगर आप ये वाली सरफेस डिस्कस कर रहे हैं तो ये वाला वेक्टर होगा, ओके. और टेंजेंशियल कंपोनेंट्स, वो कंपोनेंट्स जो कि उसके साथ साथ ट्रेवल कर रहे हैं, उनकी वैल्यू जो है वो 0 होगी. नेक्स्ट स्टेप पर हम किसी डाई इलेक्ट्रिक को स्टैटिक इलेक्ट्रिक फील्ड में रखकर देखते हैं कि उसके साथ क्या होता है. इलेक्ट्रिक फील्ड जो कि हमने जिस इलेक्ट्रिक फील्ड में हमने किसी डाई इलेक्ट्रिक को रखा है, तो उस इलेक्ट्रिक फील्ड के साथ क्या होता है. ओके, लेट्स एज देयर आर नो free charges, just like we discussed in the conductors. So there is not any kind of thing that interior of the dielectric will be empty and all the charges will go on, all the story that we just have discussed, because they don't have free charges. Dielectrics don't have the free charges, but dielectric have the charges, although they are very strongly bound to the nucleus, okay, or the bounding body. But still, because of the electric field, in which the dielectric has place, let me draw. Let's suppose, instead of drawing the 3D, I am just going to draw a 2D picture. Okay, as there are bound charges, positive or negative, whatsoever there are. So, what will the electric field effect, or how this electric field will be affected by this dielectric? This electric field will exert a force on this bound charges and displace them a little bit and make a kind of group, a kind of bounding, which is called dipole. The force placed on a dielectric material will displace the positive and negative charges a very little bit, a very small distance, and polarize them in a group. Okay. Although this dipole moment is very less, it's approximately 10 to the power minus 30, minus 35, depending upon the dielectric material as well. And in some materials that polarization is permanent, and in some materials this dipole moment is temporary. it's not our topic of discussion now. So back to the topic. Okay, moreover, that electric field will produce a torque on these charges, these created dipoles, and aligned them in the direction of electric field. Okay, it might be the case earlier that this will be not. But second thing that it happens, it gives us, yeah, it aligned, it produced a torque and aligned the dipoles that it has created in the direction of the electric field. Now let's suppose that we have n number of dipoles, okay, in a very small volume, limit delta V tends to 0. Then let's introduce another quantity, a volume density, which is called polarization vector. Okay, it is capital P and it's a vector quantity, polarization vector. Sum of all the dipoles that have been created in the smallest possible volume, in a given volume, will define the polarization vector. Yes. K is equal to 1 and delta. Okay. You could consider any small volume, smallest possible volume, and number of dipoles created in this, it will give us the polarization vector. In order to find out the flux or lines which are passing because of this polarization vector, it is experimentally verified, and theoretically we have derived it that it will be equal to charge density, but this is not the charge density that we have already encountered. It is the polarized charge densities. We are talking about these terms now. Okay, so we have just introduced another charge density, which is formulated or which is produced because of the dipoles that have been created in a dielectric medium which is placed in an electric field environment. Okay, यानी कि अभी तक जो हमने चार्ज डेंसिटी देखी थी, del dot E is equal to rho over epsilon naught. फ्री स्पेस में आपके पास जो चार्जेस की वैल्यू थी किसी भी स्मॉलेस्ट पॉसिबल वॉल्यूम में, ठीक, वो आपके फ्लक्स को, इलेक्ट्रिक फील्ड लाइंस जितनी फ्लो कर रही थी उनको डिफाइन कर रहा होता था, ठीक, या इलेक्ट्रिक फील्ड लाइंस डिपेंड करेंगी कितना आपके पास चार्ज रखा हुआ है, जो इसके बाद फिर आप नेक्स्ट स्टेप पे गॉसेस लॉ पर चले गए थे। लेकिन अब हमारे पास एक और चार्ज डेंसिटी आ गई है जो कि डाइइलेक्ट्रिक मटेरियल की वजह से आ गई है, ठीक। इसका मतलब ये हुआ कि हमें अपने इस एक्सप्रेशन को रीडिफाइन करना होगा ताकि ये एक्सप्रेशन हर तरह के मटेरियल के लिए ट्रू हो जाए, ठीक है। रिमेंबर टुडे वी जस्ट इंट्रोड्यूस दैट, टुडे वी क्लेम दैट वी आर गोइंग to place some materials in the electric field, in a static electric field, and before that we were just studying the free space, okay, and we said that let's see how that dielectric or conductors or dielectric and conductors will affect our fundamental postulates or our formulas that we have already used. So this time we are moving towards this claim, okay, कि किस तरह से डाइलेक्ट्रिक या इलेक्ट्रिक्स या मटेरियल मीडियम्स जो कि हम किसी स्टैटिक इलेक्ट्रिक फील्ड में रखते हैं हमारे काम को, हमारे जो फंडामेंटल पोस्टुलेट्स हैं उनको किस तरह से मुतासिर कर सकता है। बिफोर moving forward, let me correct that I just missed that negative sign with the dipole charge density, polarized charge density, and we have already discussed in depth in the last lecture that why we introduce this negative sign in the expressions. Okay, so back to the topic that we have. But in dielectrics we have another charge density, so there must be this rho of E with which of the symbol is minus or positive. Okay, so del dot E is a vector term. Rho minus, okay, this was like this, okay, rho minus p. Now I put the value of, if I take it, on other side, del dot rho, okay, permittivity of the free space, electric field plus polarization vector, okay, that we have that give us a collective amount of dipoles in a given volume. Okay. Now here I am going to introduce the second basic quantity we related to the field. We have already discussed that basic quantity is 4 related to the sources and 4 related to the effects. We just use one, electric field, and the second quantity that we are going to introduce is electric flux density, which is represented by D. Okay, so electric flux density is the quantity which tells us, which informs us about the behavior of electric field in any kind of material, in dielectric or in conductor wire. Okay, so it is a generic term as compared to the electric field intensity. D is equal to okay. So del dot D is equal to rho column per meter cube. It is the change in fundamental postulates in differential form. Before that we had discussed del dot E. It was the fundamental postulate. Del dot E is equal to electric field charge density divided by the free space permittivity. But now it has moved in this way. Okay, and consequently when we deal with the integral form, because as I said when we were introducing and discussing the fundamental postulates of electrostatic, that integral forms of the fundamental postulates are more important than the differential form, because we are interested in complete geometry rather than a point or a location. So when we integrate on both sides, there will be volume integral on both sides. On divergence theorem will convert that volume integral in the surface integral. So it will be d dot d of s, the surface on the left hand side, and charge density, volume charge density over complete volume will give us the total amount of charge, okay, in columns. It's in columns. Column, the unit of column. So these are the fundamental postulates in any material. Okay. No, you don't need to worry or don't need to differentiate that whether you are dealing in the conductor or you are dealing in the dielectric or in the free space. You could use that del dot D is equal to rho of free. Okay, and d dot d of s is equal to total amount of charge q. Before going to close this topic, as I said that you no need to worry about the discussion of the material. For example, if there is a dielectric, then you will have to put the amount of polarization vector here. If it is not the dielectric, then polarization vector will be equal to 0. Instead of using, most of the time we don't have information about the medium, that is dielectric or it is conductor, or we don't know the polarization vector. Okay, this term is also equal to epsilon naught epsilon r E. It is the relative permittivity of the respective material in which the electric field is placed, or in which material electric field is placed in which material. Okay, both sides. Okay, so this will, for example, I place a copper cylinder in the electrostatic field, or I place an aluminium cylinder in the electrostatic field, or I place a wooden box in the electrostatic field, I should have the relative permittivity of that material or glass whatsoever. I am going to skip the derivation from this to this. There is another term, epsilon naught psi p over E. You have to put it here, and then it's not in scope of our undergrad studies, so it is more comprehensive and most frequently used term or definition of electric flux density. D is equal to epsilon E, and epsilon means epsilon naught epsilon r. Okay, remember in circuit theory we have already discussed that this will be the error of concept, okay, not a mathematical error, that epsilon when you are when there is a written, until and unless they don't tell you that epsilon is equal to epsilon naught. Epsilon is equal to epsilon naught permittivity of the free space multiplied by the relative permittivity of the respective material. Okay, so हमने ये आज ड्राइव किया कि अगर आपके पास बजाय इसके कि आप फ्री स्पेस के अंदर डिस्कशंस करें, अगर आपके पास चार्जेस या इलेक्ट्रिक फील्ड किसी मटेरियल मीडियम मिसाल के तौर पर कंडक्टर या मिसाल के तौर पर इंडक्टर के अंदर रखा हुआ है, तो फिर भी इलेक्ट्रिक फील्ड और चार्जेस के इफेक्ट्स होते हैं और हमें इसको भी स्टडी करना चाहिए। तो पहले फेज में हमने देखा कि जो कंडक्टर्स हैं उनके अंदरूनी साइड पर, उनकी अंदरूनी सतह पर कोई भी चार्जेस और इलेक्ट्रिक फील्ड नहीं होता, उनकी सतह के ऊपर इलेक्ट्रिक फील्ड होते हैं और चार्जेस भी होते हैं। और इलेक्ट्रिक फील्ड में भी सिर्फ और सिर्फ एक कंपोनेंट जो कि नॉर्मल डायरेक्शन में होता है वो एग्जिस्ट करेगा, और वो उसका मैग्नीट्यूड डिपेंड करेगा जितने भी चार्जेस उस सतह के ऊपर आए हैं। ठीक है जी। उसके बाद हमने डाइलेक्ट्रिक की बात की, तो हमने कहा कि वहां पर इलेक्ट्रिक डाइपोल्स जो हैं वो बन जाते हैं अगर किसी डाइलेक्ट्रिक मटेरियल को आप रखते हैं इलेक्ट्रिक फील्ड में या चार्जेस उसके अंदर प्रोड्यूस करने की कोशिश करते हैं। और उसके बाद फिर हमने बहुत इंपॉर्टेंट एक क्वांटिटी जो कि हमारी सेकंड फंडामेंटल सेकंड बेसिक क्वांटिटी है इलेक्ट्रिक फ्लक्स डेंसिटी, उसको ड्राइव किया, जो कि डिपेंड करती है परमिटिविटी ऑफ द परमिटिविटी जो कि इलेक्ट्रिक प्रॉपर्टी है, परमिटिविटी ऑफ द मटेरियल इन विच यू आर गोइंग टू डिस्क्राइब परमिटिविटी ऑफ द फ्री स्पेस और इलेक्ट्रिक फील्ड के। ठीक, इस वजह से हमारे फंडामेंटल पोस्टुलेट नंबर 1 जो था वो चेंज हुए, और वो डेल डॉट ई की बजाय डेल डॉट डी में कन्वर्ट हो गया। सिमिलरली जो उसकी इंटीग्रल फॉर्म थी वो ई डॉट डी ऑफ एस की बजाय डी डॉट डी ऑफ एस में कन्वर्ट हो गई। ओके, आज का लेक्चर जो था वो इसलिए इम्पोर्टेंट था कि यहाँ पर हमने पहली दफ़ा दो मुख्तलिफ मटीरियल्स को डिस्कस किया, और हमने कहा कि अगर एक मटीरियल से दूसरे मटीरियल में इलेक्ट्रिक फील्ड जाता है तो वो किस तरह से जाएगा, जिसको हमने कहा कि बाउंड्री कंडीशन, कि बाउंड्री के ऊपर कैसे हालात होंगे। बाउंड्री कंडीशन हमारा नेक्स्ट टॉपिक है जहाँ पर हम जेनेरिक बाउंड्री कंडीशंस को भी डिस्कस करेंगे, और उसको आज हमने इंट्रोड्यूस किया है। चूँकि टॉपिक है तो हम उस डिटेल में सारी इसका इंट्रोडक्शन और उसकी इंपॉर्टेंस बताएंगे। यहाँ पे सिर्फ इतना कहना ज़रूरी है कि इस टॉपिक से अगला टॉपिक कनेक्टेड है, आपको ये वाला टॉपिक जो है उसको सही तरीके से देख के आना है नेक्स्ट टाइम, क्योंकि अगला टॉपिक बाउंड्री कंडीशन जान के लाई जा सकती है इलेक्ट्रोमैग्नेटिक्स की। ठीक, इलेक्ट्रोमैग्नेटिक्स माइनस बाउंड्री कंडीशन विल बी अप्रॉक्सीमेटली इक्वल टू 0। ओके, उम्मीद करता हूँ कि आप सब लोग अपनी हिफाजत करेंगे और अपने आप को इस बीमारी से सेफ रखने के लिए अपने घरों में ही कायम दायम रहेंगे। अल्लाह हाफिज़।